Let's now discuss ways we can make amines, and we're going to start with reactions that we are familiar with. One of the reactions we previously discussed was conversion of a primary or secondary alkyl halide through an SN2 reaction with sodium cyanide to have access to a nitrile. The thionyl group would attack the carbon with the leaving group to do a substitution reaction. Reduction of the nitrile with lithium aluminum hydride will give us a primary amine. Note that this route will always give us a primary amine. Another way to make amines would be starting with a carboxylic acid, adding thionyl chloride to convert the OH into a chloride. And then if we add ammonia or another amine, we can do a substitution reaction to give us an amide. If we use ammonia, we will get an NH2 group on the amide. If we use a primary or secondary amine, we would have a substituted amide here. Reduction of the carbonyl of the amide with lithium aluminum hydride will give us the amine. If we use ammonia in the beginning to make the amide, we're going to end up with a primary amine. If we use other amines in this acyl substitution reaction instead of ammonia, we're going to get secondary or tertiary amines instead. If we have a nitro group, we can reduce it into an amine. For example, an aryl nitro group can be reduced with hydrogenation. Hydrogen and platinum or other metal catalysts will reduce the nitro group into this aniline. The nitro group can also be reduced under metal reduction. For example, tin dichloride and an acid like HCl will give us an aniline. Other metals will do the same reaction like tin and iron as well. In this question, we want to propose a structure for either a nitrile or an amide that could be used as a reactant in order to make N-ethyl aniline, which is shown here. In this question, we want to make N-ethyl aniline, which is this compound here, from a reduction of either a nitrile or an amide. If we were going to use a amide, we could use this amide. If we add a carbonyl at the carbon next to the nitrogen, and we reduce it with lithium aluminum hydride, we'll have access now to an ethyl aniline. In this particular example, we cannot use a nitrile, so the nitrile that perhaps we can try to use would be this one, benzonitrile. However, when we reduce this benzonitrile, we would obtain aniline instead of N-ethyl aniline. So at least in this example, from a nitrile, we would not have direct access to an ethyl aniline. We would have to do another reaction in order to add the ethyl group. Another method to make primary amines is by an azide reduction. Azide is an anion that has 3 nitrogens and is actually a nucleophile. And so we can use it with primary and secondary alkyl halides to do an SN2 reaction, where the azide attacks the carbon with the leaving group to give us an alkyl azide. We can reduce this functional group similar to nitro groups by using lithium aluminum hydride, for example, and that would give us a primary amine plus, although it's not shown here, nitrogen gas, which is N2. Another method to make amines is by something called reductive amination. This is a reaction where we combine two reactions in one. We first convert a ketone or an aldehyde into an imine, which we then reduce with a reducing agent to give us an amine. Here is a general example using a ketone. If we add ammonia and sodium borohydride, we can end up with a primary amine. The ammonia would replace the carbonyl, give us an imine, which is then reduced. The double bond of the imine is reduced into a single bonded carbon to nitrogen bond. If we use a primary amine instead of ammonia, we end up with a secondary amine. And if we use a secondary amine, we will have now a tertiary amine. Here's another example using a ketone. If we add ammonia and sodium borohydride, or we combine the reaction with another reducing agent, which is hydrogen gas plus a metal catalyst like nickel, we can reduce the imine into an amine, as shown here. Here's the mechanism for a reductive amination. It starts off with ammonia or the amine that we're using, either primary or secondary amine, attacking the carbonyl. The oxygen will be protonated by an acid. That would give us initially a carbonyl amine intermediate. The nitrogen will eventually form a double bond, so the lone pair on the nitrogen will form a double bond between the nitrogen and carbon by eliminating the OH group. That gives us an imine. This is a reaction that we covered in a previous chapter. So any aldehyde or ketone, when you react it with ammonia or a primary amine, you typically will get an imine. If we reduce that imine double bond with sodium borohydride or hydrogen and nickel or some other metal catalyst, we can obtain now a saturated product, which would be an amine. A related reducing agent to sodium borohydride is sodium cyanoborohydride, which has a cyano group. The cyano group essentially reduces the reactivity of this hydride reagent slightly compared to sodium borohydride. And this is an ideal reducing agent for reductive amination. It has been found that the reaction can be done all of one single reaction. Combining ammonia, for example, with an aldehyde will give you an imine initially, which would then be reduced by sodium cyanoborohydride to give us a primary amine. Note that this reaction is typically done at slightly acidic pH, somewhere around 3 to 4. Here's another example with a primary amine reacting with a ketone. Sodium cyanoborohydride at a low pH will lead to a secondary amine. And the last example is a secondary amine with an aldehyde with reducing conditions will give us a tertiary amine. There are many biological examples of reductive amination. Here's an example using the biosynthesis of the amino acid proline. Starting with this compound, which has both an aldehyde and an amino group. The amino group, notice, is protonated, and the carboxylic acid is deprotonated due to physiological pH. The amino group can attack the aldehyde, and after removal of a water molecule, so the carbonyl, what remains from it, which is an OH group, is removed as a water molecule. we end up with an iminium ion, which is related to amines. That iminium ion can be reduced by NADH, which is a reducing agent that is found in biological cells. A hydride is added to this carbon to give us proline. In this question, we want to predict the product of a reductive amination between ammonia, acetaldehyde, and sodium borohydride. In this reaction, ammonia will replace the carbonyl and initially give you an imine that looks like this. That imine will be reduced by sodium borohydride into ethylamine, as shown on the product side. In this question, we want to predict which reactants we would use to make N-ethyl 2-phenylethylamine, which is shown here, through a reductive amination reaction. Reductive amination reactions generally combines an amine or ammonia with either an aldehyde or a ketone. And after reduction, we end up with an amine that has an extra alkyl group compared to the amine that we use to synthesize the product from the reaction. In other words, when we look at the product, we can consider the amine coming from the nitrogen attached to either of the two alkyl groups that are in the product, and we add the other alkyl group from either an aldehyde or a ketone. So in this example, we can add this phenyl ring plus the two carbons that are attached to the nitrogen from an aldehyde. If we mix it with methylamine and sodium borohydride, or we can add the methyl group from an aldehyde, so that would be formaldehyde, adding it to this amine, and sodium borohydride would give us the same product. Another reaction that is used to make amines, especially primary amines, is the Hofmann rearrangement. This is a reaction that starts off with an amide, and we lose a carbon in the process, the carbonyl essentially of the amide, by using a halogen like Br2 or Cl2 and a strong base such as sodium hydroxide. Here's an example with a primary amide. If we use sodium hydroxide, bromine, and do the reaction in water, we can convert the amide into a primary amine with the loss of CO2. Note that essentially we have lost the carbonyl and we have joined the nitrogen to the alkyl group. In the second example, we're going to use again a primary amide, add sodium hydroxide, Cl2, and water to lose CO2 from the carbonyl and join the amino group to the carbon that is to the left of the carbonyl initially. As a result, we end up with a primary amine. The mechanism of the Hofmann rearrangement involves adding base to an amide. It removes one of the hydrogens on the nitrogen, giving us a negatively charged nitrogen, which is a great nucleophile, which could attack one of the bromines of bromine, eliminate the other one. This gives us an intermediate called an N-bromoamide. The base will then remove the other proton, giving us again a negatively charged nitrogen, which can now trigger the Hofmann rearrangement. One of the resonance structures of this negatively charged amide is this structure shown here, where the negative charge, instead of being on the nitrogen, is on the oxygen of the carbonyl, and we have a double bond between the carbon and nitrogen. That oxygen can now reform the carbonyl by pushing the alkyl group to the nitrogen and eliminating the leaving group on the nitrogen. As a result, we're basically doing a 1,2 alkyl shift that is being forced by reforming the carbonyl and eliminating the leaving group. In the second part of the mechanism of the Hofmann rearrangement, after the alkyl group migrates from the carbon of the carbonyl to the nitrogen of the amide, we end up with this intermediate called an isocyanate, where we have a carbon that is double bonded to an oxygen on one side and double bonded to a nitrogen on the other side. Isocyanates are really good electrophiles. They will be attacked by the hydroxide ion. So the hydroxide ion will attack the carbon. Then the electrons in this double bond will be used to pick up a proton, which ends up on the nitrogen. That results in a carbamic acid. Carbamic acid is not a functional group we often discuss in an intro organic course, but it's a functional group that has a carbonyl, an OH on one side, and an amino group on the other side. This functional group is related to carbonic acids. Again, another functional group we don't see too often in an intro organic course, but is actually a pretty important biological molecule, especially in terms of the chemistry of blood. This is the structure of carbonic acid. It has two OH groups attached to a carbonyl. Both carbonic acid and carbamic acids are unstable and they like to decompose and form CO2. In the case of carbonic acid, we typically have a water byproduct. In the case of carbamic acid, we form an amine instead, as shown by this example. A base will remove this proton, lead to this bond, forming a double bond here. The single bond between the carbon and nitrogen will be used to pick up a proton and add it to the nitrogen. That gives us the primary amine plus CO2 as a byproduct. As we mentioned previously, in the Hofmann rearrangement, we always lose one carbon due to the loss of CO2. As an example, if we start off with a primary amide with 5 carbons, as you can see here, 1, 2, 3, 4, and 5. If we do the Hofmann rearrangement, which involves Br2 and sodium hydroxide, we'll end up with a primary amine that has only 4 carbons, 1, 2, 3, and 4. In this second example, we have a primary amide. With the Hofmann rearrangement, we end up with an amine that has only 3. We're losing the carbonyl carbon in the process, and the amine will be joined to this carbon here. In the last example, again, we have an amide that will be turned into an amine with the loss of the carbonyl carbon, and the nitrogen will be attached to the cyclohexyl group in the product. A related reaction to the Hofmann rearrangement is the Curtius rearrangement. This is a reaction that is used to make primary amines from the thermal decomposition of azo-acids with water, and it leads to the loss of a CO2 molecule. Here's an example using an azo-acid. If we heat it up, we'll get an isocyanate, which will then react with water to lose CO2 and give us a primary amine. Azo-azides is a functional group we don't see very often, and we certainly haven't seen it this semester. But azo-azides can be accessed from an acid chloride or an acid or a carboxylic acid. For example, carboxylic acid, when reacted with thionyl chloride, will be converted into an acid chloride, which can then react with sodium azide, and the azide ion, which is a good nucleophile, will replace the chlorine to give us an azo-azide. There are a lot of similarities between the mechanism of the Curtius rearrangement and the Hofmann rearrangement. In the Curtius rearrangement, we start off with an acid chloride, which when reacting with sodium azide will be converted to an azo-azide. One of the resonance structures of an azo-azide has a negative charge on this nitrogen, and it has a triple bond between these two nitrogens. In the beginning of the Curtius rearrangement, the negative charge or the lone pair on this nitrogen will be used to form a double bond here, which leads to a 1,2 alkyl shift of this alkyl group to the nitrogen by elimination of an N2 molecule. So N2 or nitrogen gas is nitrogen triple bonded to another nitrogen. The result of this reaction gives us an isocyanate, which you might recall was the key intermediate in the Hofmann rearrangement. The rest of the mechanism is essentially identical to the Hofmann rearrangement, where water or the hydroxide ion will attack the carbonyl, the carbon of this isocyanate. That will lead to the electrons in this double bond moving to the nitrogen. The nitrogen can then pick up a proton to get us to a carbamic acid. Carbamic acids, as we mentioned before, are unstable and they like to decompose into CO2 and amines. So the next set of steps simply lead to the removal of a proton from this oxygen to give us this intermediate, which will then form a double bond here between the oxygen and carbon by eliminating the amine to give us a primary amine and also CO2 as a byproduct. Similarly to the Hofmann rearrangement, the Curtius rearrangement always leads to the loss of one carbon as a CO2 molecule. If we start off with an azo-azide that has 5 carbons and we heat it, we'll get a isocyanate, and then water will react with the isocyanate to lead to the loss of CO2 and an amine that has only 4 carbons, as this example shows, since we lost one carbon as a CO2 molecule. The next example has 4 carbons in the longest chain. If we heat it, we get an isocyanate, which when it reacts with water leads to the loss of CO2, plus an amine that has only 3 carbons in the longest chain. Note that we have essentially transferred a nitrogen from the azo-azide directly to this carbon here with the loss of the CO2 or the carbonyl. Last example, we have a cyclohexyl group. If we heat this azo-azide, we'll get an isocyanate, which when it reacts with water will give us an amine and a CO2 molecule. The Curtius rearrangement is a reaction that has been around for a long time and has been used for the synthesis of several molecules. For example, it has been used to synthesize the antidepressant drug shown here. This synthesis starts off with an acid chloride, which when it reacts with sodium azide will be converted into the azo-azide group, and I'm going to abbreviate the alkyl chain as an R group. this azo-A side will be heated. That would lead to the conversion of this azo-A side into an isocyanate. So there's a carbon here. That's double bonded to the first nitrogen of the A side. And the R group that was originally on the carbonyl on the left side will shift. We'll do a 1-2 shift from this carbon to the first nitrogen of the A side. The two other nitrogens will be lost as CO2, not CO2, nitrogen gas, excuse me. And then lastly, when we add water, we're going to turn this isocyanate into a carbamic acid, which decomposes and loses CO2. As a result, this nitrogen and R group will be found in the product as shown here. How could the following amine be prepared from 4-methylbenzoic acid using the Curtius rearrangement or the Hofmann rearrangement? So the question is asking us to synthesize this aniline, or another way of looking at it, a primary amine, from 4-methylbenzoic acid, which is this compound here. This question is asking us to convert 4-methyl benzoic acid into 4-methylaniline, which is shown here. And we want to use a Curtius or a Hofmann rearrangement to do this reaction. If we start off with a carboxylic acid, we can convert it into an acid chloride, which then, if we react it with ammonia, would give us a primary amide. That allows us to now do the Hofmann rearrangement by adding Br2 or Cl2 plus sodium hydroxide, which would then lead to the Hofmann rearrangement, which always involves the removal of the carbonyl as a Cl2 molecule and joining the amino group of the amide with the alkyl group on the left side of the carbonyl, which in this case is a toluene ring. That provides one way to get to 4-methylaniline. The other way would be to react acid chloride with sodium azide, which will give us an azo-azide. Heating the azo-azide in water will lead to the Curtius rearrangement and conversion into 4-methylaniline. In this question, we want to take orthomethylphenylacetic acid, which is the molecule shown here, and convert it through a Hofmann or Curtius rearrangement into orthomethylbenzylamine, which is the following compound, where we have a benzyl group, which is a benzene plus a CH2 attached to an amino group and an orthomethyl group here as well. In order to do the Hofmann or Curtius rearrangement, we want to take this carboxylic acid and convert it into an acid chloride first, which will allow us to make the precursors of both reactions. Adding ammonia to an acid chloride would give us a primary amide. So in other words, we'll have an NH2 group here instead of the chlorine. Then adding bromine plus base We can do the Hopkin rearrangement where we lose the carbonyl, and the NH2 group will attach directly to this carbon to give us the amine product that we want. In the Curtius rearrangement, we want to convert this acid chloride that we originally have and add sodium azide to give us an azide group. Instead of this chlorine. Heating the reaction in water, we'll do the Curtius rearrangement, where the alkyl group transfers to the first nitrogen of the azide, eliminates the other two, and after the water adds to the isocyanate, we end up with the Curtius product, which is this amine group here.